Hello guys, our project is the path tracking control for JetBot based on MPC. My name is Richard Li, and we also have Jiawei Lin, David Chao, Shiming Xu, and Shikai Zheng. In order to achieve the goal of path following, we have divided this project into several components, which are path planning, MPC, and vision recognition. Before we jump into the details, let me introduce the setup of our devices as well as the flow of this presentation. The robot is actually running on a game board on the floor, which is under a top view camera fixed on a shelf. The camera is used to take photo at the beginning of the path planning process to identify any obstacles and also turn that information into constraints. The MPC then uses this information for reference tracking. And in this presentation, we'll be talking about the system dynamics, MPC, game board setup, and path planning. Now let my colleague discuss the system dynamics first.
Okay, here's the system dynamics equation, which is based on the kinematics of the robot. It involves the position and orientation of the robots, and as well as the angular velocity of both wheels. Here's the Euler discretization equation with the sampling time of Ts. Z is the inputs of the Z is the states of the robots, and U is the inputs of the robots. Below the equation below is the state space realization of the model. Next.
The constrained finite time optical control within the MPC is as following. In this CFTOC, instead of having the restrict terminal constraint, we're minimizing the distance between the current states and the terminal states, which makes the movement of the robot smoother. And we also found some issue with regard to heading angle. Next step, please. So we actually find some issue with respect to the heading angle during the path following. Since the optimal path only contains XY coordinates of the path, the robot will always try to face to the same desired heading angle as we defined at the beginning of this process. So therefore, we actually chose to interpolate heading angles to generate a set of heading angles which has the same dimension as the points of the optimal path. And the angles are the planned trajectory from the current point to the next point. By doing so, we'll have the same set of heading angle as the optimal path. And since the optimal path is made of a set of discrete points, we use, so we will both use them for the path following process. Next slide, please. The MPC algorithm is actually pretty easy to understand. So at first we will have to initialize our vehicle and also the simulation. And then the while loop is actually where the MPC is implemented. While the vehicle is not at its terminal states, we first pick next states from the optimal path as terminal set in the current iteration. And then we have to calculate a distance called ds between these two adjacent points. We will then use this ds for determining whether we have to iterate the terminal state or not. And then the optimal input is obtained from the MPC, which is based on the vehicle dynamics and also the terminal set. And then we have to update the vehicle states with the first input in the optimal input set. And then we have to calculate another distance called dv between the vehicle and the terminal set. So how do we determine whether or not to iterate the terminal set from the optimal path? So if dv is less or equal than 5% of ds, then we say the vehicle is close enough to the point we wanted to get, and then we can choose the next point from optimal path set to be our next terminal set. So the MPC can keep running. Or if dv is not less or equal than 5% of ds, we keep the current terminal set. So we let MPC keep running until the 5% goal is achieved. Next slide, please.
So we use a top view camera to construct a map of the game board for our JetBot to operate. First, we need to put 4 Aruko tags on the corners of the game board and another tag on the JetBot itself. Then we use the tags on the corners to compute a homography transformation matrix that transforms, that transforms camera coordinates to real-world coordinates. We then use the tag on our JetBot and the homography transformation matrix to estimate the position and orientation of our JetBot and feed the JetBot state information to the MPC. Next slide, please. This is a demo of how the homography is done. So on the left, you can see this is a picture taken by the camera, and scenes are in camera frame. On the four sides, there are 4 RU tags, and we can use homography to transform it to the right picture, which everything is centered. And we can see in the middle, there's this is our JetBot RU tag, and it can calculate the position and the orientation of the JetBot and feed that to the MPC. Next slide, please.
In order to make sure the JetBot can follow the path and avoid the obstacles, we detect obstacles with the camera. We designed and made a bracket which is used to hold the camera. The bracket is designed such that the camera can include an area approximately 40 inch by 40 inch. At the beginning, we would run the camera to take a picture from the top view. This picture would include all the obstacles. Then, the taken picture will be transferred into the threshold picture. Because the obstacles are chosen to have different colors from our background, the obstacles would differ from the background in the threshold picture. Then, we make the rectangular contours around the obstacles. With these contours and the coordinates, we can get the information of the location of the obstacles. With those information, we can form our constraint for our MPC with proper transformation matrix. Previous slide, please. This method of finding position of obstacles can still have some disadvantage. One is that it only works for static obstacles since the picture was just taken once at the beginning, and the color of the obstacles need to be different from our background. We will try to improve this in the future. Next slide. Here is the example. The left is the taken picture, and the right is the threshold picture, which shows the contours of the obstacles. Next slide, please.
When it comes to the path paneling part, we use the formula F equal G plus H to find the shortest path. In this formula, F is the total cost of the node. G is the distance between the current node and the start node. H is the heuristic, estimated distance from the current node to the end node. Next slide, please. We put the formula into the A-star algorithm. And in this algorithm, which is used for generating shortest path as reference, the topology of the car is captured by a top view camera, and the position of the JetBot and obstacle is found. The camera result is converted into a grid with given resolution. The grid, starting position, and the destination are the input of the algorithm, and the output of the algorithm is the shortest path, which is calculated by minimize the total cost of the node shown in the figure. Next slide, please. In the end, we got the result. We have achieved the goal to let the JetBot follow a calculated optimal path from its initial position to its desired position, and the graph we got in the end is very close to the optimal path. Thank you.